The citric acid cycle is an incredible metabolic pathway, and it's so incredible that scientists do things in order to track the flow of carbons through the cycle. They can use heavy isotopes of carbon to actually track these carbons as they flow through. And one of the most interesting things about the citric acid cycle and when you're tracking things is that you bring in two carbons from acetyl-CoA, and each turn around this cycle, you're losing two carbons. But you're not losing those two carbons that you just brought in from the acetyl-CoA. In fact, it actually is going to take you at least three turns of the cycle in order to get rid of those two carbons that you brought in from the acetyl-CoA. Like those exact two carbons, it's going to take you at least three turns of the cycle. The first time around, you're only going to lose the carbons that were already there. The second time around, you'll lose one of them. And then the third time around, you have a 50-50 chance of losing that other one, that original one that you had brought in from that original acetyl-CoA. And so we'll go through the cycle and see why this is and see how we can have kind of different fates depending on which way a molecule flips. This succinate gets flippy. We have the symmetrical molecule at one point in the pathway, the succinate. And so depending on which way the enzyme binds to the molecule succinate, then the future steps are going to be different. The end products will be different in terms of where the labels end up. And so we have asymmetrical molecules, we have a symmetrical molecule, and then we have asymmetrical molecules. And so at the symmetrical molecule step, that is where things can get really jumbled. But that symmetrical step is after you've already lost the carbons. So let's go through a cycle and then we'll go through other cycles and see, hopefully this will start making a little bit of sense. So we have a citric acid cycle, and here I'm just showing the carbons colored so that you can keep track of the carbons and not worry about the actual chemical structures right now. But if we think about the number of carbons and where they're coming from, so say we take glucose and we do glycolysis and we end up with pyruvate. Pyruvate, we would get two pyruvates from glucose, and each of those pyruvates would have three carbons. Only two carbons are actually going to enter the cycle, and they're going to enter the cycle as acetyl-CoA. The third carbon, which corresponds to carbons 3 and 4 of glucose, is actually going to leave before you enter the citric acid cycle. It's going to leave as CO2. And now you have acetyl-CoA that can join up with the 4-carbon oxaloacetate. I have in boxes the carbons that are actually going to get lost. And so we saw this one got lost. And now we're going to lose kind of the top and the bottom carbons of our oxaloacetate. So our carbon 1 and our carbon 4 of the oxaloacetate that were already present in this pathway. So we're going to lose the old carbon dioxides. We're going to lose the old carbons as carbon dioxide. And then we're going to be left with the molecule that has half of the old and half of the new. And so what you want to think about is that the acetyl-CoA is going to come in, and it's going to come in and bind to the second carbon of oxaloacetate. And that's going to push this first carbon out. It's then going to get pushed all the way out as CO2 after we do a little bit of chemistry to make that more favorable. We lose that as CO2. And then we're going to lose the bottom carbon. The bottom carbon is where we're actually going to stick on that CoA group and then remove the CoA group. But that is where we're going to be, is actually in this bottom carbon. This bottom carbon gets lost. And then this is now our new bottom carbon, which is going to be attached to the CoA and then a phosphate. And then you basically transfer that phosphate onto GDP to get GTP. And now you have this symmetrical succinate. And here's where the things are going to get tricky the next turnaround, because we have this molecule and then we have this molecule. So now we have two different fates that we need to follow. But we saw that we lost the carbons from the original oxaloacetate in this turn of the cycle. We're always going to lose the carbons that were already present, not the new carbons that we brought in. But now these red carbons that we brought in, well, now they are part of the oxaloacetate that's already present in the cycle when you bring in the next pyruvate. And so if we think about round 2, well, now we have two different options. So we need to think about, okay, we have this oxaloacetate and we could have it flipped like this or flipped like this so that we have the first acetyl-CoA, that red one, we have that on top or we have it on bottom. And if we have it on top, we'll lose it and then we'll lose the older one. And if we have it on bottom, we'll lose the older one first and then this red one. But we're going to lose them both either way, regardless of which of these two options for our oxaloacetate we started with. We're not going to lose the ones from the yellow, that fresh acetyl-CoA that we just bring in. We're not going to lose its carbons. We are going to lose, however, one of the newer carbons that we had brought in the last cycle, one of the red ones, and one of the ones that the red ones were already adding to. And now we have 4 different options at the end of this cycle, because remember, we think about, we add these yellows on top of here, but we add them to the second carbon. We lose this first carbon, we lose the last carbon of our oxaloacetate. And then we'll end up with the newer ones kind of on top of this and this, but on top of can also mean basically at the succinate, when it flips over, you get something like this and something like this. And for this one, similarly, you get this and this. So what we had different here was that we're either losing the red and then the gray. So we're losing the newer one and then the older one, or we're losing the older one and then the newer one. But either way, we're losing one of each. Round 3, however, things get more complicated, because round 3, we say, okay, well, now we have this molecule. We've got 2 of the newer ones. We're always going to, at the end, have half of it be the acetyl-CoA that we just brought in, and one of those is going to get lost. And now the question is, are we going to lose one of the quote-unquote original oxaloacetates or one of the ones from the first acetyl-CoA that we've got in? And that's just going to depend on which orientation things are in. And so if we compare this and this, we can see that here we have a gray on the end and a yellow on the end. And we'll have that on both of these. So a gray on one end and a yellow on the other end. And remember that the end ones here are going to be the ones that are going to get lost. So we're going to lose a gray and a yellow. We're either going to lose it yellow-gray or we're going to lose it gray-yellow, but we'll lose a gray and a yellow. We would not have lost that one from that first acetyl-CoA that we had brought in. Even though it has 2 carbons and each turn of the cycle, we lose 2 carbons, we can see that after 3 rounds for this one, we still have the carbon that's remaining from that original acetyl-CoA that we brought in. But if we were to choose this molecule, well, now we see that when we have this after the second round, we're going to have a red on the one side and a yellow on one end. And so we lose the end, so we're using a yellow and a red, or we're losing a red then a yellow. But either way, we're going to be losing that carbon from the acetyl-CoA that we had brought in that first round. So it takes us at least 3 rounds to get rid of the carbons from that acetyl-CoA that we brought in, those specific ones. And so you can go and you can actually follow through the different options, and it's kind of fun. So I recommend that you do that, like a little coloring activity or something. But this is kind of how the scenarios can play out. And so you can now imagine the next round, things would get even more complicated when you have to think about, okay, well, now am I finally going to lose that carbon from that acetyl-CoA? And so if you look at these products, you can see that in this case, you would lose that carbon from that red acetyl-CoA because it's on the end. But in this case, you still want it. So there is a lot of complications once you get further down, but the key things are that first turn of the cycle, you're not going to lose any of the new ones. The second turn, you'll lose one of the newer ones. But remember, newer is referring to the first one that you brought in, not to the fresh one that you brought in. And then in the third round, you may or you may not lose that first acetyl-CoA that you brought in, its second carbon.